Think Tank recently visited a major symposium held at the American Enterprise Institute. It is said that the 21st century will be the century of biotechnology. The topic before this House, the promise and purpose of genetic research. This week on Think Tank. In 1953, two men, James Watson and Francis Crick, revealed that they had mapped the DNA molecule, the instructions for all life. Since then, scientists have used that map in a treasure hunt for cures, vaccines, and treatments for most everything that ails us. Many scientists believe that in the next few decades, unlocking the human genetic code will benefit people's lives more than any other scientific endeavor. Will we see greatly extended human life expectancy? Will there be cures and preventions for such diseases as Alzheimer's, Parkinson's, cancer? Will we understand learning disabilities? Will we be able to repair damage to the brain?
Irreducible level, one gene, one protein, can ask questions now. What are that collection of...
The American Enterprise Institute Conference tried to decode the future of DNA research.
While it is natural and valuable for geneticists to explain their work with all of the excitement and enthusiasm they feel for it, it is also important that they not exaggerate or overpromise. In particular, it is important that new developments and future prospects be described with all of their surrounding uncertainties, that failures be candidly acknowledged, and that heavy emphasis be placed on actual demonstrated advances rather than future promises.
Featured at the conference were two pioneers in the biotech revolution, William Haseltine, the founder and president of Human Genome Sciences, Inc., and Anthony Fauci, director of the National Institute of Allergy and Infectious Disease at the National Institutes of Health. We asked both scientists to describe what to expect from the biotech revolution and to prescribe the best policies for getting there. Dr. William Haseltine is chairman and CEO of Human Genome Sciences, a company at the forefront of the biotech revolution. They patent genes and have filed for over 185 patent applications. Bill Haseltine was formerly the director of cancer pharmacology at the Dana-Farber Cancer Institute at Harvard University.
Bill Haseltine, we all hear so much about DNA and biotech. What happens if it works?
If the revolution, the modern revolution in biology works, we lead healthier, longer lives. The impact of the new revolution in biology is to create new means to predict, detect, prevent, treat, and I believe ultimately cure many of the major ills of man.
For example, tell me, let's say it's not 1997, but it's 2027. I'm giving you 30 years?
30 years.
30 years. What is it that you or I might have in the way of illness that if we went to a doctor today, he'd say, sorry, and that he'll be able to say, here's what?
I think the fundamental presumption is different. You won't go to a doctor because you're sick. You will go to a doctor because you don't want to become sick. You will have a battery of predictive and early detection tests which replace what we now know as our annual health check. That will lead to a series of prescriptions which will be really lifestyle prescriptions. Some of them may involve medicine, but not all of them. Those will, by and large, prevent diseases that might occur from occurring or ward off diseases that are in their earliest stages. And so rather than going to a doctor when we're sick, we'll be going to doctors to continue our good health.
In your list, you did say cure also.
Well, there's a lot of things that can happen to people. Let me give you a small example from our current work. we have isolated that substance, which is normally used by your body to repair injuries to the skin, that is, deep injuries that cut not only the surface layers, such as a scrape, but the deeper layers, such as a knife cut or an open sore or a burn. The same substance, by the way, is used to repair the lining of your gastrointestinal tract. Well, we have found in our experiments, not in people, but our preclinical experiments, that that substance can very rapidly accelerate the healing of wounds of many types that have been inflicted. Whether it's a cut, whether it's a burn, whether it's a recision of the intestine, you get a much more rapid, better patch than you would without it. That's the type of medicine that I'm referring to.
Since the work of Watson and Crick, is what is going on now just sort of filling in the blanks? We got the big picture, and now it's going down the array of question marks, or are there tangents and brand new paths that you're still discovering?
Well, that's a very interesting question about what is new and what isn't. Is there an end to knowledge? And I recently wrote a chapter for a book called The Microverse. And in there I divide biology, post-war biology, into two great eras. One which is the Watson and Crick era, DNA goes to RNA, goes to protein, and the working out of that. But there's a second one, which is just as profound, which is all the differences that happen after that. And how we're built is just as much a part of the DNA that we are as to what happens once that information is read out. The genetics is just one part of our individual variation. What happens to a gene once it's read from the DNA storehouse, we now know is quite complex. Genes are considered to be like a rope, and each of us can individually cut and paste that rope differently, so that the major things that control, for example, mood, the target of serotonin reuptake, the Prozac target, is actually cut and pasted differently in different people. We have found in the brain a gene that most people inherit in each and every person we look at. It's tailored differently. It's almost as if a tailor is cutting a suit for you from the raw genetic material. And finally, for those who are overly concerned about genetic predetermination, let me say the more we learn from studies of the brain, the more we're learning that we are a set of potentials that are actually reacting to the environment all the time, and our brain is constantly being remodeled based on our experience. It's not that we have a fixed organ called the brain.
Right.
It's we have an organ called the brain, which is a set of potentials, which templates around real experience.
What is the answer to the question as to whether we're just filling in the blanks after Watson and Crick, or
We
whether
are
there
not
new...
filling in the blanks. There are great stretches of new information that are qualitatively different from what was perceived to be the case, say in the 60s when I was trained.
Dr. Anthony Fauci, a Brooklyn native, is at the forefront of AIDS and human immunoregulation research. He oversees a massive research project at NIH with roughly 1,300 employees and a $1.3 billion budget. What benefits can we expect?
There will be immediate benefits. There will be curiosities and greater understanding with no necessary benefits, and then there will be long-term benefits. You have to look at it, I'll look at it from my vantage point as a biomedical researcher and a physician who's interested in human disease. So you can take the revolution in DNA technology, and you can talk about the production of products, the production of drugs in a massive quantities by recombinant DNA technology. That's one thing. But if you look purely, for example, at health, you can talk about diagnostics, being able to diagnose disease with a degree of sensitivity and specificity that we would never have imagined prior to the availability of these molecular techniques. You can talk about the development of new drugs by using the power of recombinant DNA technology. You could talk about the development of vaccines.
Let's just talk about new drugs for a
Right.
moment. What sort of afflictions would we be able to deal with 30 years from now that we can't deal with now?
Well, it
I
isn't
mean, and I know you're guessing.
No,
I mean,
it
we're
isn't
not- right,
necessarily
right.
that you can't deal with, but that
Well,
you can deal with in a much more efficient
Okay,
manner.
right.
For example, there are a host of human diseases where there is the lack of or an abnormal protein or substance that the body needs. And you can't just make the body produce this. You have to supply the body with the right machinery to do it.
Well, what sorts of
For
diseases?
example,
Names.
Diabetes and insulin, to be able to treat diseases that require a certain component, growth hormones, other types of hormones that are deficient or abnormal in an individual, by providing, under the right circumstances, the genetic basis for producing the protein. By inserting a particular amount of genetic material into an individual, you can actually correct defects that were unimaginable with regard to being able to correct them. There are congenital abnormalities of individuals, for example, who have cystic fibrosis, who have an abnormal gene that doesn't allow the proper production of a variety of substances, salts or what have you, that's needed in order to have proper physiological function of a cell. The potential to correct that. There are hematological diseases like sickle cell anemia and thalassemia. There's congenital immunodeficiency diseases. All of these will be benefited sooner or later. The trick is to be able to get the DNA technology to the right level where you can actually have a positive impact on the health of an individual.
Will, in a decade or 2 or 3 from now, will people who have access to modern medicine still be dying of AIDS?
Well, I think there certainly will still be people who will die of AIDS, but if you look at the advances that have been made in therapies based on understanding the molecular makeup of the virus itself, I think that will be something that will be far, far less common than it is now, not to mention the use of DNA technology to develop, hopefully, a safe and effective vaccine that you might have rather efficient prevention of HIV infection, the same way that you have prevention of polio.
Would that be a vaccine that is introduced after a person has HIV but before they have AIDS?
Either. The most classic paradigm is to vaccinate someone before they get infected with a microbe. But you might still, if you get someone whose level of virus is suppressed effectively by drug, you may be able to vaccinate that person to build up the body's own immune response so that when you withdraw the drug, the body can continue to suppress the virus. All of those things are possible.
The biotech revolution may lead to some startling accomplishments, but what policies will best advance the forthcoming scientific breakthroughs?
Now, you are a scientist capitalist or a capitalist scientist.
Well, at any rate, I'm an entrepreneur
You are an entrepreneur
and a scientist.
Your company patents genes,
Yes, we do.
and some people say, shame on you for patenting
No.
genes.
Virtually no informed person says shame on us for patenting genes. Supreme Court ruled in 1981 that genes and living forms, if they are true creations of man and they are useful, are the fit subject for patent material, or should be fit subjects for patents. And indeed, around the world, all patent offices not only patent living organisms, they allow the patenting of genes. There are many businesses.
But do you patent new genes, recombinant genes, splice genes, or do you, or as if I know what I'm talking about, or do you patent existing genes? I mean, I can't patent my ear. Say, I'm patenting
You probably
an ear.
should. It's unusual.
It is unusual. I mean, so are you patenting a gene that already existed? Evander Holyfield might want it, but anyway, yeah.
Be able to repair his genes.
Right.
His
But-
ears, yes.
Right.
No, but well, let's talk about what a patent is. A patent allows you, first of all, in order to have a patent, you have to find something new that's previously not conceived. Second of all, you have to demonstrate its utility. But above all, you have to teach a useful art. Most people think patents mean they're secret. It's exactly the opposite. Patents were actually invented by the Venetians to allow them to take technology from the Middle East and sell products to the north of Europe. And so they would import an artisan, and they said, if you teach us how to do whatever you know how to do, make green glass, we will give you a 20-year exclusivity to make green glass. You'll be the only one that's able to make and sell it, if and only if you teach us how to do it. That remains today the primary purpose of patents, to allow people to take what they would have held secret, share those secrets, and still have commercial protection for the fruits of their invention. So the heart of a patent is sharing of that knowledge and teaching, not keeping it secret. The alternative for that Middle Eastern green glass maker was to hold that secret and pass it only on to his son or daughter when he died. The patent system is designed to protect the small inventor and to allow them to share so all of society can move forward. Most people don't realize that the key communication for our technical world is the patent application.
Do some of your fellow scientists give you grief over this? I mean,
Not anymore.
Not
They
anymore.
first thought, when we first set up the company, because we had such a, we created a tool that could find and make useful many genes at once, people were concerned. They then raised the concern, should we patent genes at all? After further consideration, the scientific community as a whole has now come to the conclusion that provided we meet the criteria of patentability, which is novelty, utility, and teaching how to use it, genes should be patented. I think it's almost a universal conclusion, even from those who used to be our most severe critics.
You are sort of, in your corporeal form here, trying to sort of marry Francis Bacon and Adam Smith. Is that the idea, saying that the way to maximize the utility of this new knowledge is to do it through the entrepreneurial sector, where you can raise capital, where you can marshal forces, and say there is not a conflict between Francis and Adam?
I think that's one way of putting it. The other way of putting it would be to say that you couldn't have created this knowledge in an existing institution. Universities weren't appropriate and would not tolerate it. It was actually kicked out of the government. Big pharmaceutical companies let it lie fallow. We're very fortunate that in the US we have this healthy entrepreneurial sector, and I think that's the sector that allowed it to happen.
Of course, it's not just entrepreneurialism. Tony Fauci emphasizes that industry, government, and the academy must work together. He cites the development of new treatments for AIDS, such as protease inhibitors, as an example of the collaborative approach.
All of that took place in a very truncated period of time, very, very rapidly, unusually rapid for the development of a drug. It was a beautiful example of several things. One, the transition from fundamental basic research to a usable product, a very effective drug against HIV, and also that consortia between industry, government, and academia. This is a very good example that I think is going to go into the textbooks of historical examples of how those things work together.
Where does someone like Bill Haseltine fit in? Is he sort of the moderator between, or the gray area between pure and applied, and sort of takes the whole pure stuff and sort of refines it and jiggles it and
I think that's
sells
a good,
off some of it to the
the biotech industry, and certainly human genome sciences as a prototype of that, is an example of a company that can do very elegant basic research and immediately translate it into something.
So you have pure research, and then you have these gray area intermediary companies, and then they are providing the commercial pharmaceutical companies, for example, Amgen, which happens to underwrite this program, and all the others, the Bristol Myers and the Pfizers and the Mercks, and they get it through that pipeline, and then they go out hell-bent for leather and say, boom, we're going to make a product, And in this case, in the case of AIDS,
Right.
you say it happened remarkably quickly,
Right.
textbook fashion.
Right.
Question: did it happen in this disease because of the intense political pressure of the gay community?
No, I don't think that it happened because of that. Certainly, the constituency groups played a role in focusing and intensifying attention of the general public, the Congress, the administrations, several administrations, on the problem. I don't think it happened because of that. We had an epidemic that was emerging to have global impact. We had scientific opportunities in an area that actually was very exciting and potentially very important research that was something that people were interested in working on because it was very important, clearly important from the standpoint of public health, but also was an area of research that had enormous opportunities. So I believe that when you talk about how things evolved in the AIDS epidemic is certainly not a unidimensional thing.
The case is made, and you hear it in a political context, that, and particularly in the HIV situation, that the drug companies are making too much money on these drugs and people can't afford them, and you know that argument also. Right. How do you come out on that?
You really have to take it case by case, but one of the things I believe that is not appreciated by the general public is something that understandably is difficult to appreciate. When a product is made, not infrequently the drug companies, the pharmaceutical companies, invest an extraordinary amount of money into candidates that never pan out. So they're spending tens and sometimes hundreds of millions of dollars on candidate A, B, C, D, and E that never make it. Then when candidate F or G comes along that becomes a drug, it becomes necessary for them to recoup not only the investments, but also to make a profit so that they continue in a fashion to be able to exist, pay their stockholders or what have you. As a biomedical researcher that isn't someone in a pharmaceutical company, I can understand how people look at that askance and say, gee, why are they charging so much or why are they making so much money? But in fairness to them, I think you need to look at the extraordinary investment that's made by the pharmaceutical industry in research and development.
Is there a competition or a jealousy, sort of a locker room feud between industry, government, and academia in these fields?
I don't think so at all. I think there's always competition in science, but it's competition that generally, with few exceptions, is a healthy, energizing competition where.
But the researchers at NIH, you and your colleagues, are making a decent living wage. But you're
hardly,
hardly right. I didn't want to. I mean, I don't want to get into politics. But your colleagues on the private side, and particularly those who have started their own companies or got a royalty arrangement, I mean, these people either are or on their way to becoming extremely wealthy men and women.
Yeah. I have to tell you that really is not a consideration. We all have our choices. Those of us who want to stay with the government are doing it because of the extraordinary opportunities we have to do science in an atmosphere that's very conducive to doing science.
What happens when your wife says, who's going to pay the tuitions?
Then you make a decision. You make a decision, are you going to stay or are you going to go? But while you're doing it, you don't say, well, gee, I wish I could be doing something else. You make up your mind what you're going to do. I happen to have made a decision in life that I want to be a researcher in an atmosphere that happens to be an atmosphere where you don't make a lot of money. But the rewards that I get intellectually and as a feeling of accomplishment far outweigh financial compensation.
Thank you very much, and thank you. For Think Tank, I'm Ben Wattenberg.
We at Think Tank depend on your views to make our show better. Please send your questions and comments to New River Media, 1150 17th Street Northwest, Washington, D.C. 20036. or email us at thinktank@pbs.org. To learn more about Think Tank, visit PBS online at www.pbs.org. And please let us know where you watch Think Tank. This has been a production of BJW Incorporated in association with New River Media, which are solely responsible for its content.